Hello. Yeah, we wrote a new linker for Mach-O, which is the file format used on macOS and iOS and whatnot. And we're here to talk. We're here to talk to you about it. So this is Jess, who works at Meta, and he's mostly interested in iterative development speed for iOS apps. And he wrote most of the LD Mach-O code. I'm Nico. I work on Chrome at Google, and Chrome is built on many platforms, and we used to use basically one dedicated compiler per platform, which was a huge pain. So over time, we moved to like a single compiler Clang on all the platforms, and we also moved to a single linker and a single build system and whatnot. And while we did that, we had to like build some of those tools, and we noticed that in many cases, we were able to build tools that were like up to an order of magnitude faster than the tools that we replaced, which was nice. And I probably wrote like the second most code of LLD for Mach-O. So what's LLD? LLD is a linker. I won't tell you what a linker does. And for LLD, we have like, what we think is very important for a linker is mostly that it's very fast. And that the code is fairly simple. And you could look at this and be like, well, obviously, like everybody wants this, but there's an actual trade-off here. So one thing we don't think is very important, at least for now, is flexibility or being able to run, to use this as a library or stuff like that. We want to write a very fast linker. And this is, so there's already an ELF port of LD and a COF port of LD, and they're kind of like separate programs, and Jess will talk about this later. And they are fairly independent, which means each of the ports is like fairly simple and only does what it needs, and it's fairly fast for that reason. And so that's like kind of like the philosophy behind LD. For each of the ports has a command line. So LD is like a binary, and then you have a symlink LD-link that points to it, and a symlink LD64.LD and LD.LD. And depending on which symlink you call the binary through, it's command line compatible either with link.exe, the Visual Studio linker, or with BFD-LD, like the normal ELF linker, or in our case with LD64, which is the Apple linker. So if you like just call that symlink, you can like pass exactly the same flags that you would pass to LD64, and things should just work. Or on Windows, you usually call the linker through the client compiler driver, and then you just pass -fuse-LD equals LD. And our linker is called, and this is fairly easy to do. So if you just want to give it a try and see how it works for your project, it should be like a 3-minute thing, hopefully. So LD64, Apple's Mach-O linker, is already pretty good. Like in Chrome, it was the linker that gave us the least amount of trouble. It's fairly fast. It's deterministic. So why even bother? So one reason for us in Chrome was that we already built Clang and LD for the other platforms of LLVM trunk and bundle that and send that to all the bots and all the developers. And we're able to fix bugs very quickly. So one thing we wanted to do is use response files, which is basically a file that stores all the command line flags that you pass to the linker. And LD64 added that in, I think, Xcode 12. But if you actually use it, it crashed. And then we had to like wait, like we had to report this, wait a year for this to be released in Xcode, and it was kind of frustrating. And if it was just part of LLVM, we could have like done that in a week. Another effect of LD being part of the LLVM repository is that compiler driver Clang and LD know that they're at the same revision, so they can work together more tightly. So one example, for example, if you build a C++ program but you use Clang instead of Clang++ to link, then you get like pages and pages of undefined undefined symbol errors about, I don't know, stream and stuff. And so one thing that we don't do at the moment, but that you could imagine doing, is the compiler driver could pass a flag to the linker that says, if you see any linker errors, then try linking with the C++ library. And if that works, while the normal link doesn't, then emit like this message. And that'd be a much nicer user experience, for example. Another example is if you want to do a safe identical constant folding, you need this address significance table that stores the names of all the functions that have their address taken. And there's a pending patch to add that for LD, actually. And that makes, like, if the compiler and the linker are at the same version, that's easy to do. Like, you don't have to, like, add it to the linker, then wait and do difficult dances. On the same note, LTO is much easier. like we tried to use link time optimization in Chrome over the years, like many times, and always failed before we switched to this linker, which in part might be incompetence on our part, but we tried really hard. And yeah, and then also performance. So as I said, LD64 is already pretty fast, but we were able to like write way faster linkers on other platforms. So let's see what happens. So this is on some Chromebot that links the browser tests binary, which is the biggest binary in Chrome. It links like all the browser code and lots of tests code. And link time like went down a lot when we switched from LD64 to LD. So it's like 3 to 4 times as fast. It's like not a 10x improvement for us, but it's still like fairly nice, I guess. And we even haven't optimized LD all that much. It doesn't do like many things in parallel that it could do, like input file reading, I think. Like the code that is there is, I think, pretty fast, and we do look at performance, but we haven't like, there's still like many wins to be had. And this is not just in Chrome, this is data that Keith Smiley at Lyft collected. This is linking Envoy proxy, which is like a mesh service proxy. So there we go from like 45-ish seconds with LD64 to maybe 6 seconds. So that's like 8 times, so getting close to the 10x win there. And the bigger your binary is, the bigger the win usually is, and the more C++ you use, the bigger the win usually is, I think. And it's also like for the Lyft app on iOS, it's like 3x a win. For Clang, it's a little less than 2x. So the smaller your Chrome gets, the smaller the win is, but still, it's quite a bit faster than LD64. And ZLD is Michael Heisel's, I think, fork of LD64 that uses more efficient hash tables. And we're like way faster than that too. And what about, for Chrome, we switched the default linker in Chrome 95, which I think went live late last year. So if you use Chrome on a Mac, it's now linked by LLD for Mac. And in Chrome 99, we enabled thin LTO, which gave us a 6-ish% win on speedometer. And this is and we wrote like a bunch of blog posts about this, which triggered a press cycle. And so you have like lots of tech press articles that mention thin LTO, which I think is a little bit funny. And this is basically a speedometer score in Chrome over the last, 60 versions. There's like a bit of a jump when we switch from an Intel machine to a Mac, to an ARM machine. And thin LTO is like one of the bigger jumps, and it's also the one that got us above like 300, which is, I think, Chrome on ARM is basically the first hardware browser combination that got this score over 300. And this is like some synthetic benchmark score, but this also translated in actual user visible metric wins in Google Docs and whatnot. So we use this in Chrome at Google. We're about to use it for YouTube and Maps for iOS for development builds. Then Meta uses it for development builds at iOS. Lyft uses it. And if you build any binaries, any larger binaries for iOS or macOS, maybe you're interested in looking at it too. And with this, I'll hand it over to Jess.
Thanks, Nico. Now I'll give a high-level overview of the design. Code-wise, LLD is a collection of 3 largely separate linkers. The reason behind that is that the COV, ELF, and Mach-O formats have so many differences that most code sharing just isn't worth it. All we share is basic utility code. Here is a truncated list of all the differences between the formats. Don't worry, I know there's a lot on this slide, but I'm not going to dive into each of them. I just want to underscore how difficult it would be to have a common abstraction over all these differences. The bottom line is that LLD has chosen to favor concretion over abstraction. This means less indirection, less marshalling of data, and therefore better linker performance. Additionally, most of our internal data structures have the same names as their counterparts in the Mach-O file format. This ties back into our goal of hackability. Someone familiar with the file format, but not the LLD code base, should nonetheless be able to ramp up quickly. Next, I want to talk about some quirks of the Mach-O format. But first, let me give you an overview of the linker's operations to show you how things fit together. The operation of the linker can largely be broken down into 6 steps. First, we read in our inputs and perform LTO. Then, we split each object file's sections along symbol boundaries. This splitting is something unique to the Mach-O format, and I will speak more about that shortly. The 4th step is to perform symbol resolution, where we load various files from archives to satisfy our symbol references. Assuming we've resolved all symbol references successfully, we now have enough information to emit a working binary. However, for release builds, we want to make sure the binary we emit is as small as possible. So we follow up by performing the linker's 2 most important optimizations, stripping dead code and identical code folding, or ICF for short. And finally, we write our output binary. So now, as you can see, we've only parallelized a small number of these steps. What this means is that there is a lot more opportunities for optimization and further speed increases. So now that you have a sense of what the linker does, let me dive into 2 of Mach-O's format-specific quirks: subsections via symbols and the embedded add-ins. So, what is subsections via symbols? Well, as I mentioned, LLD splits each section into subsections at symbol boundaries. And each subsection acts semantically like an individual section. Roughly speaking, it means that each function ends up in its own section. So on the right, we have an assembly snippet containing 3 different symbols. The subsections via symbols directive causes the linker to implicitly insert each one into its own section, like so. This allows us to optimize functions piecemeal. For example, we can remove a function if it's dead, or merge 2 identical functions. In contrast, if we did not have this directive, we will only be able to remove a function if all the other functions in the same section were dead, which in practice almost never happens. In our initial implementation of this feature, we created a new section struct for every subsection, and we copied the common section data each time. Later on, we improved this by having each subsection share a common metadata struct. The memory and copying savings from this gave us a 2.5% speed up. Subsections via symbols is truly one of the unique advantages of the Mach-O format. ELF, in contrast, does not have this feature, and so is forced to emulate it at a compiler level. The F function sections flag causes Clang to emit each function in its own section explicitly. While this does achieve the same result, it means that the linker has to ingest significantly more object file data. Another clever optimization we did involves the assignment of relocations into their subsections. So each section has an associated list of relocations. Now, when we split that section up, we need to match these relocations with their corresponding subsections. We have the list of subsections sorted by address naturally. However, we have no such sorting guarantees for the relocations. Therefore, our initial implementation performed a binary search over the list of subsections for each relocation. Later on, however, I noticed that MC always emits relocations in address order. Thus, in practice, we can actually perform assignment relocation in ON time. Making this change gave us another 2.3% speedup. However, there's a catch. LD-R does not emit sorted relocations, so a fallback to the binary search path is still required. Now you may be wondering, what is LD-R? And that is what I'm going to talk about next. The -R flag tells the linker to consume several individual object files and emit a single object file. This object file can actually be used as input into another linking step. As you might expect, this is typically used to package libraries. Unfortunately, LD64's -R output has several subtle differences compared to MC's. As a result, LLD has to use several additional code paths just to handle LD64's output. We would love to drop the support at some time, but it won't happen anytime soon. First, LLD itself does not yet support -R. And even if we did, LD-R's output is often encountered when importing third-party libraries, over which the developer has no direct control of. All that said, we would love to discuss some of these differences with Apple Linker folks, and perhaps they can be resolved in a future version of LD64 and enable us to streamline LLD's code. Now I'm going to move on to the other challenge that we had to handle for the Mach-O format. To recap, what ICF does is it deduplicates identical function bodies as well as read-only data. It does this by comparing the section contents as well as the relocations for each section. However, due to the Mach-O format, comparing section contents is actually slightly tricky. What complicates it is that relocation data may be embedded in the section contents. Let me illustrate with an example. On the left, we have an assembly file with two functions, foo and bar, and two more functions that reference them. If foo and bar are identical, we can see that refs foo and refs bar must also be identical and folded by ICF. However, let us see what happens when we run this assembly through MC. So what we get on the right is a conceptual representation of the binary object file. And we have two relocations which tell us that refs foo and refs bar need to have fixups applied so that they can refer to the right addresses of foo and bar. However, the relocations themselves do not contain the addresses of foo and bar. Instead, those addresses are embedded as add-ins directly inside refs foo and refs bar. So in this example, since bar is at address 0x10, refs bar has the value of 0x10. As a result, if we naively compare the section contents, we will incorrectly conclude that refs foo and refs bar can never be identical. So how do we resolve this? We would like to overwrite the embedded add-ins with zeros, enabling us to see that refs foo and refs bar are identical. However, the first problem is that LLVM memory buffer, which we use to read in the files, only exposes a read-only interface because it is backed by mmap. Now we could overhaul memory buffer to use map private and copy on write, but first, that's a huge refactor, and second, the copying is slow, even though the kernel does optimize it somewhat with the copy on write. The thing is that there are a lot of embedded add-ins in any binary, yet only a small number of them are actually impeding code folding. Because most of the time, if the add-ins are different, there's usually something else in the same function that causes the functions to be different. So as a compromise, we whitelisted two sections which we knew were severely impeded, where ICF was severely impeded due to these add-ins. In particular, that's the compact unwind section and the Objective-C class ref section. So this is all well and good. However, it's worth noting that ELF does not have this problem for newer architectures, like ARM64 and x86-64. For those architectures, it has the Rela relocation format, which has no embedded add-ins. And so it would be worth looking into modifying the Mach-O format in a future iteration so that we can further simplify LLD's code. All right, having talked about all the things that LLD can do, let me talk about some things it can't. Here's a brief list of the features we know are lacking. In general, we haven't prioritized them either because they are for target platforms that are too new or too old. So chain fix-ups is an example of something that is for a newer platform. Chain fix-ups allows a more compact encoding of fix-ups and therefore smaller binaries. However, it's only available for iOS 15 and above, and since most people are still targeting iOS 11 or 12, we are not in a great hurry to implement it yet. Another thing we are lacking is support for 32-bit platforms like x86 and ARM32. For x86 in particular, we are quite unlikely to ever implement it, given that most modern platforms have moved on from it. The code complexity that it adds just doesn't seem worth it. And that's where we are. In summary, LLD is 3 to 4 times as fast as LD64 at 1/5 the code, and most things even work. I would like to give a shout out to Rui and Peter for the early code prototype of LLD Mach-O, which provided us a great starting point. And I would also like to thank all those who have contributed to the code base in the last 2 years. There are way too many of them for me to list here, but we couldn't have done it without all of you. And we are really looking forward to adoption by the community. And if you guys run into any bugs or if you have any great performance improvements, please let us know. All right, let's open it up to the floor for questions and answers. Thank you.
Any questions from the audience?
I have a quick question for Jez. You showed the linker step, and you mentioned that LTO code generation is done before simple resolution. And it was not clear to me how it is semantically consistent with regular linking, because, for example, you can have LTO files in static archive that should only be pulled in the link after simple resolution, like if simple is used from there.
Yes, these steps are actually not strictly sequential. When we load more files through simple resolution, then we do the conversion, and then we do the splitting. So this is a simplified model of what actually occurs. So you are right, yes.
Okay, thanks. I was not sure if there was something specific to Mach-O that was different, but okay, thank you.
Yeah.
Any other questions? Great. Thank you so much.
Thank you.
Thanks.